Jnanam Paramam Dheyam. Knowledge is supreme.
Okay. This is the theorem that we proved also earlier. The same proof here also, Hilbert's theorem, that says that this for any ideal A in the polynomial ring, this Hilbert series is a rational function whose denominator is 1 minus t power n minus 1 n plus 1 and being a polynomial with integer coefficients a k t k, and therefore h small a, this m is a polynomial function for large n, and that polynomial one denotes by p suffix a, and this is a polynomial with rational coefficients. This polynomial is called Hilbert polynomial or Hilbert-Samuel polynomial. For A. All right. Now, the most important fact. This is only observation. So I had recalled all these things. So suppose now I have two ideals A and B. Ideals such that these two algebras are isomorphic, k x1 x2 xn mod A and k y1 y2 yd mod B. Suppose these are isomorphic as k algebras. So this is then we are denoting by A, this is we are denoting by B, and this k small y1 to yd, and this was k small x1 to xn. And then what we need to prove is P, the polynomial PA, we have associated polynomial PA here PB, and then we have seen in earlier example that they are not same polynomials, but we want to prove that they are the same degree. So degree of this equal to degree of this is what we need to prove. So we have this isomorphism. That means these small y's are coming from some polynomial, right. Therefore, let us call the yi, small yi, they are coming from some gi. And let us take these gi's are polynomials. So let us look at their degrees, degree of g1, degree of gt, and let us take their maximum, call it k. Then what do we want to check? Actually, how are you going to check these two polynomials of the same degree? What one will prove is this is polynomial for large m, this is polynomial for large m, and so we have to look at HA at m and HB at somebody. So let me use the next page. So let us take any m, and I want to now prove that the relation between HB of m and HA of this k is a fixed constant here, km. I want to find the relation between these two numbers, and I will prove this is less equal to. So, for large m, and again interchange the roles. So, one will be less than other, and so that will give the equality on the degree. So, how do I prove this? So, what was this? So, this is what I am trying to prove. So, what is this by definition? This is by definition what involved is b less equal to m. This is the dimension of b less equal to m. That was the definition. If you remember, when B is the finite type algebra generated by y1 to yd, B suffix less equal to m is you take all polynomials in y's of degree up to m and you collect them. So, that was evaluate them at small y's and collect them. So, this was the definition, and here it was dimension of k over k, a suffix less equal to km. This was the definition, and I want to prove this. So, I should be proving that, so enough to prove that this vector space B less equal to m is a subspace of phi of A less equal to km. See, phi is an isomorphism, that was phi, this isomorphism is phi. So, whenever I have somebody here, I just push it there, and that is an isomorphism. So, this, if I prove that this is a subspace of this, then this dimension will be less equal to this dimension, but because phi is an isomorphism, this dimension will be equal to this dimension. So, I only have to prove that this is contained here, right. This is correctly, this is image of this, it is contained in B. So, that contains this subspace. So, if I prove that, then we are done. So, what do I have to prove? That means, if I have any element here, any element will look like what? Any element will look like h of y. Maybe I should use some other letter, say capital G of y, where G is a polynomial of degree less equal to m, and then we have evaluated at y means we have read the image of G in B. So, this polynomial and so this is same as G y1 yd, but these y1 yd they are coming from those g's, small g's, right. So, this is same as G of y1 is coming as a phi image of G1. So, that is phi of G1, phi of GD, correct, because you remember this, we have lifted these y's we have lifted here. So, y1 is coming from G1 under phi. So, therefore, this is correct, but now this phi is an algebra homomorphism. So, I can take phi outside. So, this is same as phi of G, G1, GD. So, here is a polynomial of degree less equal to m, and in that variables we have substituted G1 to GD, and G1 to GD are polynomials of some degrees and k is the maximum. So, what can the polynomial, this polynomial cannot have degree more than k times that original. So, that is this. So, that proves this inclusion. So, therefore, we are done. So, altogether we have done that what we have proved is degree of HA and degree of HB, they are same. So, we have proved that this degree does not depend on an algebra generating set for the finite type algebra. Okay. The next is, now we are almost done. Now use this degree. So, this degree gives one hand the dimension of A and the other hand dimension of the graded ring. So, now I will just leave it for you to tie it up. So, now conclude, little checking is needed, but that I will leave it to you. Conclude that dimension of R, dimension of A when A is local, AM local, then dimension of A and dimension of GR M A, they are same. Okay. Now, that proves one of the thing, and now I will prove this is also very important to prove the normality, because normality is usually proved by a lot of complicated stuff, and later on we will use more complicated when we have machinery to deduce it easily. So, the theorem now I want to prove is A local, and suppose GR MA is normal domain, then A is normal domain. In particular, so in particular will be regular local rings are normal. A regular local implies A normal. Because we have seen a regular means graded ring is polynomial ring, therefore polynomial is normal, therefore A is normal. Okay, so proof is not difficult, but it is little tricky. So, we have first note that A is the integral, A is the domain, because we have seen last time if graded ring associated graded ring is domain, then A is the domain. This is we have seen last time. So, what do you want to prove now? Here you have a quotient field QA, and here you have an element A by B, where A and B are elements in A, B non-zero, and suppose this is integral over A, then I want to prove it is in A. So, if A by B is integral over A, then I want to prove, A by B belongs to A. What does that mean? That is you want to prove that the element A belongs to the ideal generated by B. This is what we want to do, because if it is ideal generated by B, then A is a multiple of B, and then you can cancel B. And done. So, we want to prove this. For proving this, it is enough to prove that the element A belongs to powers of m power n plus b for all n. That is where I will use Krull's intersection theorem. Which says that in a Noetherian local ring, if you take the powers of m and intersect them, it is 0. Okay, so we want to prove this. So, I want to prove this for all n. To prove this, all right. This I am going to prove it by induction on n. If n equal to 0, it is clear, because if n equal to 0, m power 0 is ideal the ring itself and nothing to prove. So, I assume n is bigger than equal to 1, and then by induction hypothesis I can certainly write this A as m power n minus 1 plus ideal generated by B. This is by induction hypothesis. So, that means A I can write it as some element in m power n minus 1, that is A tilde, plus some multiple of B, that is R times B, where A tilde belongs to m power n minus 1 and R belongs to A. All right. Now, if this A prime is already in the next power, we are done. So, if A tilde is in m power n then we are done. Otherwise what? Otherwise it is exactly here. So that means otherwise the order of A tilde is n minus 1. Now let me explain this term order of A tilde. So we have a graded ring here GRMA, and we have our ring here, and when we have an element here, let us say x, element is x here. How do you read it here? You have to first go to the highest power of m that x belong to, and then read mod the next power. See, if this x belong to m power n, but not in m power next power m power n plus 1, then you will read the x will read in x bar will be in m power n by m power n plus 1, and that this is the x going to x bar. That is how you read elements of A in the graded ring. But then this n has a property, this n has a property that x belong to m power n, but not the 1. So this n is called the order of x. So that is what I have written. Order of A tilde is n minus 1. That means it belongs to m power n minus 1, that is okay, but it does not belong to the next one, because if it were belonging to the next one, we are already done anyway. So that is the notation. Okay. Okay, in that case what happens? Now look at this equation and divide this equation by b. That means A by b will be equal to A tilde by b plus r. But this is same as saying rewrite it. That means A tilde by b equal to A by b minus r, and A by b were integral, r is an element in A, so it is integral over A. So therefore the difference is integral over A. So this is integral over, you see, from A by b I am making some process so that numerator becomes lesser and lesser degree, no? So modulo this. So this is integral over A. Have you heard the concept of almost integral? There are two concepts, almost integral and integral, in case of integral domain, and both are same if the ring is Noetherian. So I will recall that both are same if the ring is Noetherian, if the integral domain is Noetherian. So integral, you know, integral means it satisfies the monic polynomial with coefficients in A. Almost integral means, so an element x in A, this is a quotient field of A, x is an element here, we call it almost integral over A if there exists an element C in A such that C times x power n belongs to A for all n. That is almost integral. Now what is always true is integral implies almost. So we want to say they are equal, these concepts are equal in case when A is Noetherian. See, how do you test somebody's integral? That means you have to check that if you take the algebra generated by that element, subalgebra generated by that element, it is a finite module, right. So Ax should be finite module. This is integral. That was one of the equivalent condition from the definition of integral thing. But if it is almost integral, then what is the condition? If you want to rewrite this condition is what? That means this condition is equivalent to saying, you look at this Ax that is contained in C inverse A, which is contained in QA. You see, if this is in A, that means all powers of x will belong to A if you invert C. This condition is obviously this containment, and if everything is Noetherian, this is Noetherian because it's generated by, it's a Noetherian module, and therefore this will be Noetherian. So both these conditions in case of Noethering, they are equivalent. So now, because we have concluded that this A by B, which is A tilde by B minus R, this is integral over A. So in particular, it is almost integral. So that is equivalent to saying almost integral over A. But that will mean that there exists C in A such that this is my element x, right? This will mean that there exists a C such that C times A tilde. So from here I wanted to prove that, see what is that we want to prove? We want to prove that, this equation, no, A belonging to m power n plus b. This is what we are heading to prove. This is what we need to prove. So almost integral means there is a C, so that C times A tilde power n will belong to ideal generated by b power n. See, when you this one times some c power this, but when you calculate that, that will mean that it belongs to b power n. But then now read these equations more in a graded ring, in an associated graded ring, you have to read that. So that means if I take, so let me write for an element x in A, in GR MA, its image I want to write it GRX. So what is the GRX? That means you find a power of M where x belong to that highest power and read mod the next power, that is the GRX. So when I have this equation, so GRC times GR A tilde power n, that will belong to GR ideal generated by GR B power n, but GR B power n is this is true for every n. That will mean that when I go mod GR A tilde mod GR divided by GR B, this element power of this times the GRC, this will belong to the ring, this will belong to the quotient field of GRA. You see, therefore this element is almost integral. So GR A tilde, this proof is not difficult, but it is, you have to use some calculation. So this one is almost integral because this element exists, so that all powers belongs to this quotient field. So this is integral, almost integral, and therefore integral over GRA, but we know our assumption is this is normal, so it belongs to GRA. So GR A tilde belong to divided by GRB, this actually belongs to GRA since GRA is normal. But what does that mean? That means that where do this element by definition GR A tilde, this is by definition it is in the nth component of this ring, and nth component means the order of this A tilde. So this belongs to, therefore GRA n minus 1 and this GRB, this belongs to A suffix, no, GRA suffix order B, and therefore this quotient, this fraction is therefore homogeneous. So, these are homogeneous element of degree n minus 1, this homogeneous element of degree order B, and therefore this fraction is homogeneous of degree n minus 1 plus order B. So, that means this element is of the form GRA tilde divided by GRB, this is of the form GR of some element S, where S is of order, this order n minus 1 plus order B, that is belongs to, therefore this belongs to m power n minus 1 plus order B mod the next power m power n plus order B. So, homogeneous elements, look, they are coming from A, but this means look at GRA tilde minus GRS, you just multiply GRB, which is equal to GRA tilde minus GRSB, because that is how the product is defined in the graded ring. But this is same as this is same as A tilde minus SB, this belong to the next power. So, this is plus, no, this is the image of this element in m power n minus 1 divided by m power n. This is the image. This is the image of this element in this quotient. So, that will mean that A tilde minus A tilde, no, equal to A tilde minus SB, this minus SB, which is plus SB, this A tilde equal to this plus minus, this belongs to m power n, because the difference is, and this one belongs to B. So, we are done, right. So, just what I just say that you just, this is just an interplay between how do you read the graded ring. The structure of the graded ring is very important, how the elements from A go there and how do you read their degrees and so on. So, that proves whatever we want, and then cool space. So, by passing from A to A by A bar, which is A bar is A by ideal generated by B, then the Krull's intersection theorem will tell you what we want to get the result. But this does not use high powered machinery that again I will prove this regular local in the normal when I would have had some more vocabulary from algebra. But this is the first principle proof. Okay.